Breaking the octet rule. Lewis structures continued. The goal of this video will be to continue our discussion of Lewis structures so that you can now draw them for structures that break the octet rule. We'll want to be able to identify which elements typically break the octet rule, as well as draw Lewis structures for those atoms. Some elements commonly have less than 8 electrons. So these are beryllium, aluminum, and boron. Whenever you see these three, you should kind of think to yourself, hey, maybe I'm not going to have an octet. Maybe I'm just going to have 4 or 6 or 6. That's the typical way that those are split up. Second period elements are never, ever, ever allowed to have more than 8 electrons. And it's probably worth mentioning here, of course, that hydrogen and helium can't have more than 2. So if your hydrogen, helium, or any of that second period, you're absolutely not going to have more than 8 electrons. Seriously, don't. Now, your third period elements, they can. And the reason for this is that they have d orbitals, which you can use to create a way of having more than 8 electrons, which that'll get talked about more when we start talking about VSEPR and geometry and things of that sort. So hydrogen, helium, and second period elements absolutely cannot have more than 8 electrons. Your third period elements and below, so further down on the periodic table, those are allowed to. Now, you're going to see some that do it more often than others. So, for instance, phosphorus and sulfur, you're going to see it all the time. Iodine and xenon also. So you'll get kind of used to seeing those elements and thinking, hey, if I need to break this rule, I can have, 5 or 6 or whatever. All right, so let's do a few examples. So first we have AlH3. So we're going to start this the same way that we started it before. Nothing there has really changed. So we need to count up all of our electrons. So from aluminum, we have 3 electrons. From hydrogen, we have 1 electron, but we have 3 hydrogens. So we have 6 electrons total. Hydrogen can't be our central element, so it must be helium or aluminum, which is also denoted by the fact that it's written first. Typically, not always, but typically, the first element written is going to be your central element. So now we'll do this. And you see that hydrogen has its 2 electrons, so it's happy or stable. Aluminum, on the other hand, only has 6, but we don't have any more electrons. And you see this a lot with things like aluminum and boron and beryllium, where there simply aren't enough electrons, but that's okay. Aluminum is content to just have each of its electrons form a bond. And so this one's okay. Now, just for the sake of completeness, we should also go through and assign formal charges here. So we'll do this for both hydrogen and aluminum. Okay, so hydrogen from the periodic table has 1 electron. And here, and this we're going to do for just one, but it's the same for all of them, of course. So it gets 1 from the bond, and it doesn't have any lone pairs. So we subtract 1, and we get a formal charge of 0. For aluminum, we get 1 from each bond. Or, well, let's start with our periodic table. So we count our valence electrons, and we see that there's 3 valence electrons. And then we come over here and we look and we see, okay, well, it has 1 from each bond, and so we need to minus 3. There's no lone pairs. And so we get a total of 0. All right. Now, moving on to the next example. Now we have SF6. So we look and we say, okay, we have fluorine. Fluorine is only allowed to have 1 bond. It's a halogen, and it's that first halogen, so it's in the second period. So we'll put sulfur in the middle and the fluorines around it. Now, of course, first, got to check our electrons. So we get 6 electrons from the sulfur. We get 7 electrons from each fluorine. And there's 6 of them. And so we have a total of 48 electrons. All right, now put our sulfur in the center. And we think, okay, well, fluorine's only allowed to have 1 bond. Sulfur's, if we put an octet on it, would only have 4 at most, but we can break the octet rule here. So instead what we can do is we can put all of the fluorines around the sulfur. And then if we fill all of our fluorines, octets, and you count all of those up, I'll leave you to do that. You count all of those up, you'll see that we do in fact have 48 electrons, just like we would here. Now, just for good measure, let's check all of our formal charges. So, for our sulfur, we go to our periodic table, we see that we have 6 electrons. We subtract how many we have here, so we have 1, 2, 3, 4, 5, 6, 1 from each bond. So we subtract 6, get 0, so it's a formal charge of 0. Now each fluorine. So we go to the periodic table and we see, okay, it has 7 valence electrons. And then we come up here and we say 1, 2, 3, 4, 5, 6, 7. So we subtract off the 7. Each lone pair, it gets to keep total. And each one from the bond, it gets 1 of. Now, I'm going to take a moment here to clear up a misconception that tends to happen around this point that I see a lot of. So make sure you recognize that when we're counting electrons for an octet and when we're counting electrons for a formal charge, we're doing so very differently. When we count for an octet, we count 2, 4, 6, 8. Because it's sharing that electron. So the fluorine says, okay, well, I'm sharing both of these electrons that are in this bond. And so its octet is filled by having 2, 4, 6, 8. That's for filling octets. That's different from what we've been doing with formal charge. Remember, with formal charges, we're counting each of the lone pairs as its own. So 2, 4, 6. But from any of the bonds, it only gets 1 of them. It only gets half of the bonding electrons. Because in reality, sulfur is sharing half of that electron density. So it's 2, 4, 6, 7. So again, I just thought it worth mentioning it here now that you've had some practice at this to make sure you do notice that there's a difference. All right, next one, POCl3. So 5 electrons from the phosphorus, 6 electrons from the oxygen, 7 electrons from each of the chlorine, gives us 32 electrons. Okay. Now, this one's kind of fun. So, which one goes in the middle? Technically, it could be any of them. Now, oxygen's only allowed to have 2 bonds. Chlorine typically only has 1. It can have more, typically only 1. And the main thing is the phosphorus was written first, so that's giving you a massive hint. The other hint that goes along with this is the least electronegative element typically that goes in the center. So in this case, all of that lines up. The one with the most bonds, the least electronegative, and the first one written are all the same atom. So that's going to give us a pretty good indicator that phosphorus should go in the center. So we start out by drawing our skeletal structure. We put 1 bond to each thing, and we try to make our octet. Now, count up all these electrons. And you see you have enough. But something kind of interesting here happens when we try to figure out formal charges. So let's figure out formal charges here real quick. So we'll start with the chlorines. We have 7 electrons from the periodic table, and each one here owns 2, 4, 6, 7, or 2, 4, 6, 7, 2, 4, 6, 7. So all the chlorines are the same, and they all have a formal charge of 0. Now let's look at phosphorus. From the periodic table, we see that we have 5 electrons, and here it owns no lone pairs and 1 from each bond. So it's 4 electrons. So it's going to be a +1. Now let's look at oxygen. I'm going to shorten myself on room a little bit, so I'm just going to do it over here. Oxygen has 6 from the periodic table. And here we see it has 2, 4, 6, 7. So oxygen has a -1. Now let's look at the oxygen and the phosphorus there. Having a +1 and a -1 charge isn't necessarily a big deal. Those are low enough that it's allowed, and we'll see situations where that is the formal charge. However, remember what I said about minimizing formal charges. If you're in a situation where you can find a way to minimize them, that's what you want to do. So if we could find a way to, instead of having a +1 and a -1, get that down to 0, all of our atoms would be a little bit happier. So what we would want to do is make it so that the oxygen had less electrons that counted as its own, and phosphorus had more electrons that counted as its own, without ever actually changing the octet part of it for the oxygen. But since sulfur can break the octet, what we can do is we can take those electrons from the oxygen and use it to form a bond. And instead draw something that looks like that. Now, what you see by doing this is you're still able to make your octets. Everything is still stable. Now, let's look at our formal charges. Nothing has changed with chlorine, so I'm just going to leave that and let you see that you figured that out before. And we'll look at oxygen and phosphorus. So phosphorus, once again, 5 from the periodic table, but now you see it has 1 from each bond, so 1, 2, 3, 4, 5. And then oxygen has 6 from the periodic table, 1, 2, 3, 4, 5, 6 here. It keeps its lone pairs, 1 from each bond, 0. Okay, so now all of our formal charges are equal to 0. So phosphorus now has 2, 4, 6, 8, 10 electrons, so it broke its octet rule. It has more than 8 electrons as far as the octet counting goes, but that's okay. Phosphorus is allowed to do that. And so this is our most stable structure because of the formal charges. So after watching this video, you should now be able to recognize your common octet breaking atoms so that you have that in the back of your mind in case it comes up. You know that maybe you're not going to be following the octet rule here. You should be able to draw the Lewis structures of the molecules that break them, both from having not enough electrons and from having too many. And we're going to do a review and some harder examples in class. Make sure you know how to do these simple examples before coming, though.